Okay, so we're going to talk today about combinations and permutations, and that's the last section of this chapter. So we'll review on Thursday, and then your test will be on Friday. So your test is on Friday, which means your homework is due on Friday for sections 10.1 through 10.8. So all of that homework is due Friday. If you've not done any of it, you have a busy couple days ahead of you. All right, so let's start by talking about... Go back to what we did yesterday with the dice, where we rolled dice and we were talking about the sample space for getting doubles, right? First of all, what does doubles mean again? Two of the same thing, right? What was the first thing we had to do?
Diagram.
We had to do a tree diagram to figure out what?
The combination.
All the different possible options that we could get, right? And it's like we could roll 1, 1, 1, 2, 1, 3, 1, 4. How many were there?
36.
Close. 36. There ended up being 36 total options. We had to do that way because we needed a sample space, right? And what is a sample space? It's a list of all the possible combinations, right? So we had to write out those 36 possible combinations. But what if I just asked you for the number of possible combinations? Do you think a tree diagram is the most efficient way to do it? No. Probably not. Can you think of a way that involving 2 dice and the number 36? Can you think of a way you would have gotten 36 without having to do the tree diagram? Gabe? 6 times 6 gives you 36. Where does 6 and 6 come from?
I forgot what the thing was called.
Okay. Maybe Victoria? Each dice has how many choices? 6. So what do you do with the number of choices? Yeah, Gabe, you were making that harder than it needed to be. Each dice has 6 choices, so what do you do with the choices on both? You just multiply them, okay? So this is called the fundamental counting principle, which is basically just a fancy way of saying you can multiply the number of choices that you have to figure out the total number of combinations. This would also apply to that Subway problem that we did. Remember how we made a tree diagram for the Subway menu? And we made it a lot shorter than it could have been, but think about it, that would have been huge, right? So let's go through what that would look like in the fundamental counting principle. So again, instead of making a tree diagram, we're just going to multiply our number of options. So when you walk into Subway and you see a menu, and I'm making this up, but let's say the menu looked basic just like this.
Oh, it works.
Yeah, and what's another? Chicken?
Oh, that's my favorite.
Okay, and then cheese. We've got American, cheddar, Swiss, and pepper jack. All right, and then bread. I know this isn't in the right order, but bread, Italian, wheat, white, flat, and that's okay. Doesn't matter. Let's pretend that this Subway only has 3 meats available. All right, so we're going to stop right here. And we're going to use the fundamental counting principle to think of how many different combinations of sandwich we could get. So how many choices do I have for meat? 3. How many do I have for cheese? 4. And how many do I have for bread? So what do I do with those numbers? Just multiply them. 3 by 4 by 4. So 3 times 4 is 12. 12 times 4 is 48. So how many possible sandwich combinations could I come up with? 48. Is that the answer if I say what's the sample space? No. What would be an example from the sample space in this problem? Turkey, cheddar, wheat. Turkey, cheddar, wheat would be an example of the sample space. How many options of those would you have? Your list would be 48 different combinations. Is that something you want to do right now? Probably not. That's really excessive. So most of the time, sample space questions will be things like heads or tails, or things that are shorter you can make a quick, easy tree diagram with, whereas fundamental counting principles are things like this, where it's a lot longer because you have a lot more options. Okay, so take a look at this problem. A florist is arranging centerpieces that include 1 flower, 1 plant, and 1 vase. She has a choice between 2 vases, 2 kinds of plants, and 3 kinds of flowers to choose from. How many different centerpiece combinations are possible? So what would you do to figure that out? Multiply what?
The kinds of flowers, the kinds of plants, and the kinds of...
Okay, so how many vases?
2.
And then flowers?
2.
And then plants?
3.
All right, and what would you get when you multiply that? 12. Why?
That's 2 times 2 is 4, 4 times 3.
Good. So you have 12 different options for centerpieces. Do I ask you for the sample space? So do I care? In fact, in this problem with the florist, could you even do a sample space?
Not really.
Why
It's
not?
not saying the exact
It doesn't even tell you what kind of flowers there are. So you would have to be like flower A, flower B. You would need to give you something like roses and tulips and a square vase and a round vase and 3 different names of plants, right? So unless you have those names, you can't really do an accurate sample space. So here you're just figuring out how many possibilities there are. And that's when you can use the fundamental counting principle. Okay. So just really quickly, I want to do one other, a little bit more difficult of an example with this. So let's say, for instance, I'm making a password. All right, I'm making a password for your computer, okay? And the first 3 digits have to be letters, and the last 3 digits have to be numbers. So I want to know how many possibilities there are for that password. So first of all, I'm going to repeat that one more time, and I want you to tell me how many things are in my password. So the first 3 digits are letters, and the second 3 digits are numbers. So how long is my password? 6. It's 6. So what I always do when I start these problems is I draw 6 blanks. Okay, and then these have to be what? Letters?
Is there the possibility of technically like endless?
No.
Because like you can just like there's like infinite number.
It's not infinite though, because that's what we're going to find right here. So it's not endless. Like, it is a huge number, but it's not endless. So when you look at this, what goes in here, if we go back to the example we just did, the numbers that went in here were the choices that we had, right? So we counted up the choices that we have. So when you're going here, what are the choices for letters? A through Z, which is how many? So how many choices do I have in this spot?
24.
And how many here?
25.
Nope. And here. Okay, how come it's 26 every time, doesn't go down?
Because there's 26, there's 1 letter for each.
Does it say anything about you can't use it twice? No, it didn't say anything about that. So you can use them each time. This could be like A. All right, so you have 26 options because it's A through Z. So those are your options. What are your number options? And this is going to answer Gabe's question because Gabe made a good point. He said, aren't there infinite numbers? But why does it only have to be 0 through 9?
1,000 is already
Because it's only 1 digit. So 0 through 9. So how many choices is that? No. 10. Why? Because you have to count the 0. Okay? So there's 10 choices here, 10 choices here, and 10 choices here. Now what do you do with these 6 numbers? Those are the ones you multiply. Okay? So somebody with a calculator, do that for me. Do 26 times 26 times 26 times 10 times 10 times 10. Wait, whoa, 175,760,000. Okay, so that's the number of options. So that's 17,576,000 different possibilities for the password you could come up with. But where did we get those numbers that went into it? Where did I get 26, 26, 26, 10, 10, 10? Well, the alphabet, so kindergarten, right? So the alphabet. And then why, again, Micah, was this just 0 through 9?
Because each one is only 1.
It's only 1 digit, and those are your 1-digit numbers. So there's 10 choices. So when you're using the fundamental counting principle, you're just filling in with what your choices are. Okay? All right. So from here, we're going to use that a little bit later, but we're going to talk about combinations and permutations. And these have to do with compound events. And think to English class for a second. What's a compound sentence?
It's like a run-on.
Kind of like a run-on. It's, say it, Alfonso? 2 things put together. So a compound event is 2 events put together. So like what we talked about yesterday, when you roll 2 dice, that's a compound event because you're rolling 1 dice and you're rolling another. And those are 2 separate events. So the probabilities of them, we ended up doing like in your rewind today, you multiply the probabilities times each other. So we're talking about 2 styles of compound events today, combinations and permutations. And the difference is in a combination, the grouping of outcomes it's a grouping of outcomes, but the order does not matter. Okay? So the order of your grouping doesn't matter at all. So you basically have a choice to make, but the order doesn't matter. So, for instance, a street vendor, what's a street vendor?
Like one of those people that sell like
People who sell stuff on the street, right? Okay, so people who sell like hot dog stuff on the street. And they don't really do it here. I don't think I've ever really seen it here. But in New York, a lot of people sell nuts. Like sometimes at Christmas time you might see it, but like nuts on the street, you can get like a bag of honey roasted nuts or whatever it is. And so there are a lot of those street vendors. And this guy is selling cashews, peanuts, and almonds. But he's advertising and he wants to know how many different ways there are to mix two kinds of nuts. Okay, so two kinds of nuts. So I want you guys to give me, let's just list, what are the combinations of the different nuts that you can make using these three? Cashews and peanuts. Cashews and almonds. Okay. Yeah?
Almonds and peanuts.
Almonds and peanuts. And peanuts and cashews. Okay, I want to, Urath, for a second. You were saying almonds and cashews, and then you hesitated. Why?
Because it's the same thing.
It's the same exact thing as this one. So do we count it? No. Do we count this one? No. Do we count this one? So here, the order doesn't matter. Because if the order mattered, it would increase. So this is called a combination because essentially, if I'm thinking about what this vendor is doing, right? Basically what this vendor does is you walk up, Brian, and you're like, I'd like cashews and peanuts, please. And he takes his little scoop and he scoops into the peanuts and he puts it in a bag and then he scoops into the cashews and he puts it in the same bag, right? Do you care which one he did first? No, because you're just going to eat them, right? You're probably going to shake them around and mix it up and eat some at once, some at the other time, right? Think about when you go, how many of you guys have gone to get frozen yogurt?
Me.
Okay. All right. So you can go to Menchie's or Sweet Frog or whatever your favorite one is, or Tutti Frutti or whatever your favorite one is, and you go and you get your cup and you fill it up with yogurt and forget about the yogurt for a second, move on to the toppings, okay? I want 3 toppings. Give me one. Okay, Oreos, Hershey Kisses, and M&Ms. Okay, that's a good froyo bowl. All right. If you put M&Ms in the cup, does it matter that, like, when you put Oreos in, are you like, oh, my bowl is ruined because my Oreos are on top of my M&Ms instead of the other way around? Okay, well, you're a little OCD with your froyo. Does it really matter when you do those? No, the order doesn't matter. So we will call that a combination, okay? So we call that a combination. A permutation. I guess that's true. But pretend you're someone who doesn't really care. All right, so just general gut reaction, the order doesn't matter. Okay? Because cashews and peanuts is the same as peanuts and cashews. Okay, now a permutation is an arrangement of outcomes where the order does matter. So this girl, Karen, is painting her bedroom, and she has these choices of colors. She has orange, green, blue, and purple paint. And what she wants to do is she wants to paint the walls, and then she wants to put a stencil and put a design on the walls also. Okay? Does the order matter here? Yes? Because she needs to pick 2 different colors, right? She can't pick orange and orange, because then if she painted orange and orange, what would happen? You wouldn't see the design at all. It would just look all orange. Okay, so if she picks orange for her wall and then paints a purple design, it would look like this, right? But if she uses the same colors in a different order, does it look the same? No, it would look like this. So there, does the order matter? Yes, the order matters there. So that's called a permutation. Okay? So another way I think about this is, and I think if you have, when you come to school and you get, what do they call those things out there?
What?
They're lockers. Yes, they're lockers. What do you get?
Your textbook.
Code number.
You get a code number, which they call a combination. Is that an accurate name?
No.
I don't think it is. My argument is no, it's not an accurate name. Because in a combination, what do we say?
It's not
The order doesn't matter. Is that true on a locker combination? No, because let's say, for instance, that your locker was 12, 25, 32, right? Weird. Okay. It was 12, 35, 22. I think I just said different numbers. But is that the same as 22, 35, 12? No. So, yeah, that could be a totally different locker. So, in fact, should they call those combinations or permutations? They should actually call them permutations because the order is important. Okay, so think about Karen. Even though she's selecting orange and purple, and here she's selecting purple and orange, so is she buying the same paint colors?
Nope. Yes.
Yes, but is she ending up with the
order's not
same?
the same.
The order is not the same. It matters, right? So we say a permutation, the order matters. A combination, it doesn't. Okay? So think about something like you're having a student council election. 25 people are running, and they're running for president, vice president, secretary, and treasurer. Does the order matter there? Yes. Does the president have the same job as the secretary? No. So does the order matter there? Okay. If you're vying for first, second, or third place, do you care which one you get? Yes. You want which one?
First.
Hopefully first place. Maybe you are you like being mediocre, so maybe you don't really care. But usually you care, right? But if you're just saying, okay, when we do cahoots, and I say the top 10 people get in, and they all get 100s, do you care if you get first or 8th place? No, not really. Why not, Micah?
Because
All you care about is getting the 100, right? So does it really matter if you have first or 8th place? No. As long as you're chosen in that top 10, the order does not matter. Does that make sense? So a combination, order does not matter. Permutation, order matters. So really, those should be called locker permutations. Good. Okay, you should. I don't know. All right, so go do these 6 at your boards. Before you move, hang on. The first 2 are just fundamental counting principles. These are your choices. The headings don't count as a choice, right? Eggs is just telling you the eggs. How many choices are there? 2. Okay, not 3. All right, and then down here, don't answer the question. Just tell me if it's a C or a P. Okay, so the next little thing that we're going to talk about involves factorials, and essentially what I'm going to show you guys is a way to do these on your calculator so that you don't have to figure out combinations and permutations all using like super long fundamental counting principles, okay? So a factorial is essentially just a shorter way of writing out 5 factorial means 5 times 4 times 3 times 2 times 1. So it means 5 multiplied by everything smaller than 5 until you get to 1. Okay? So 5 times 4 times 3 times 2 times 1. Why doesn't it go all the way to 0?
Because it'll take it to 0.
Because if you multiply something by 0, it would always become 0. So it's just that number times everything through 1. And we say that's factorial. All right? And that's shown using this exclamation point. So 5 times 4 times 3 times 2 times 1 ends up giving you 120. So 5 factorial is 120. So everyone take your calculator. Okay, for those of you that listened when I said get a calculator before you go to your seats, type 5. And then look at the button below mode that says PRB. Press PRB and a menu shows up. And do you see how there's an exclamation point in slot 3?
Yeah.
Go down to slot 3 and press enter.
5, and then be on the bottom of mode. And then below mode right here.
Enter.
Just press enter.
Like this, and it shows up A and S.
Then that's not right. So did you press 5?
Why is it an exclamation?
Because that's just the symbol for it.
5, you know what they say?
Hey, Miss Bro, what are you doing?
Yeah, I know what you're saying.
You're going to ask a neighbor because I told you to have a calculator. So
Whoa, nothing. What?
okay,
I know
so
what you're thinking.
if you did not have a calculator when I explained that, please check with a neighbor. That's why I asked you guys to get them before you went to your seats. Okay. I'd like to move on, but I'm not going to do that until this talking stops.
Then PRB. Go all the way down. It's an exclamation.
Okay, so that should have given you what?
120.
120. So 5 exclamation mark, and then if you hit enter, that gives you 120. So that's allowing you to calculate factorials on your calculator. So that PRB, what do you think that stands for, perb? Based on what we've been doing for the past week. Almost. That's part of it. Think about what we've been doing the past week overall. We've been talking about theoretical and experimental what?
Theory.
So we've been talking about theoretical and experimental what? Someone just said it. Probability. So that PRB is a menu of probability stuff. So that's why it's PRB, because it stands for probability. And it's going to be where we go to do what we're going to be doing next. Okay? So 5 factorial is 120. So on your calculators, find 4 factorial and find 8 factorial. So practice doing that on your calculators. If you're not sure how, ask a neighbor. So once you have 4 factorial, somebody tell me what that is.
24.
Okay, and then what is 8 factorial?
40,320.
Say that again.
40,320.
Like that?
Yes, ma'am.
Okay, so 40,320. So factorial just means that number times all its stuff. And the reason that we use that is because, for example, if you were doing something like, I have 8 people in a room, and I want to sit them down to take a class picture, and I have 8 chairs, okay? What are all the ways that I can have them sit down? So you're basically doing what we just did before, where you've got 8 chairs, 1, 2, 3, 4, 5, 6, 7, 8. Yes. How many choices do you have for chair number 1? How many people are there?
1, 8 through 8.
How many choices do you have? 8? But the next choice, how many do you
7.
have? Why only 7?
Because there's already one seat.
Because somebody's sitting down. So they can't sit in the first seat and the second seat. So that would be 8 times 7. How many do you have here? 6.
5, 4, 3, 2, 1.
So what a factorial does is a factorial basically does all that for you. Okay? So that works out really well if you're picking 8 and you have 8 options. But it wouldn't work out so well if I had 20 of you guys and I had to seat you in a row of 8. Because if I have 20 of you guys, what does that mean if I only need 8 in the seats?
12 left over.
I have 12 people left over, and that means that they're not going to be in the seats, but could they be possible options? Yes, they could be options. So that's what we're going to talk about how to do next. So we have combinations and permutations. And there's a way to do it on your calculator so that you don't have to figure out all that stuff. So take a look at permutations. Remember, permutations, what's the difference? The order matters. The order matters. So our example of the chairs, does it matter which seat you're sitting in? No. So that would be a combination. Permutation would be like if you have 20 people running in a race, and 3 of them get medals for first place, second place, third place. Does the order matter there? Yes, because you would want first place. So you would say, okay, I have 20 people, and I have 3 spots, and this is a permutation. So on your calculators, to do this, so that you don't have to use that formula, what you can do is press 20. Now press PRB. So you're pressing 20 and then you're pressing PRB. And because it's a permutation, you're going to select NPR. So that first one. And then hit 3. So it should look like this. 20 NPR 3. And that ends up giving you what? 6,840. So that's how many that's how many permutations there are for winning first, second, and third place. So where did those numbers come from? 20 was the total choices that we had. 3 were the spots that they were vying for. And again, how come that was a permutation?
Because there's a different ways of people getting first.
You care about getting first, second, or third place, right? The order matters. Okay? So, in this example problem, Lee brings 7 CDs numbered 1 through 7 to a party. How many different ways can he choose the first 4 CDs to play? So this is a permutation because the order of the CDs matters. So how am I going to enter this into my calculator? So the first thing I decide is that it's a permutation, which means I'm going to use NPR. But what are my numbers going to be?
7.
I have 7 choices. And then how many am I choosing? 4. Good. So I'm going to do 7 NPR 4, which is 840. All right, so there's 840 permutations for ways you can select all those CDs.
Wait, how'd you get 7 CDs, right?
7 CDs,
4 is what?
and 4 is the number that he's going to play.
Oh.
So basically, your first number is your total number of choices, and 4 is the number you actually want. So in the class example, it was like we had 20 people, but 8 seats. So it'd be 20, choose 8. Okay, so this one is a combination. There are 11 different cereals for sale at the grocery store. How many different ways can a shopper select 4 cereals? Because when you're shopping for cereal and you're going down the aisle and I know I'm going to buy 4, does it matter if I put my Reese's Puffs in the cart before I put my Frosted Flakes in the cart? No. Either way, am I going home with both of those? Yes. So I don't care about the order, which means this is a what? This is a C, which makes it NCR. And what's my first number? 11. And my second number? And so when I do that on my calculator, 330. Okay? So typically, which number will be smaller, permutations or combinations? Combinations will be smaller. Think back to the nuts example and the paint example. When we made the nuts example, what did we have to do with 3 of our choices? Cross them out because the order didn't matter. They were the same thing, right? But with the paint example, which was a permutations, orange and purple was different than purple and orange, which is why permutations typically results in a bigger number, okay? So permutations is usually going to be bigger because it's very specific. So the order matters, so there's more choices because orange and purple is different than purple and orange. Okay, go at your boards, try these 4. So the first thing you need to do is decide if it's a P or a C, and then just use your calculator to figure it out.